Good afternoon, everyone. I'm Jung, a postdoc working at India. Today, I'd like to talk about our recent study where we developed a Hessian-based transfer learning approach to increase the performance of the neural network model for predicting chemical kinetics. Before I begin, I'd like to thank my co-authors and mentors, Bruno Soriano, Chen, and Muhammad Khalil from India. I believe that the data set is one of the crucial components for the development of the machine learning. And machine learning in fluid mechanics field, there are several attempts to gather data across the scientist and open to public. One example is BLASTNet. So I believe that the number of data we can get access becomes larger and larger. So here my question is how to utilize such the shared data set and potentially the pre-trained neural model in our research. In this slide, I'd like to show a simple example of how to utilize the data set and its limitation too. In my recent study, I made a conventional fully connected ANN model for capturing chemical source terms of the species transport equations, and I performed a parametric study by changing an operating condition, as you can see in this table. And the first result I'd like to show is the case where an operating condition between the training and target simulations is the same. In that case, I found that the ANN-based model shows an excellent agreement with the DNS result, while the overall computational cost significantly decreases. But this scenario is quite ideal since the operating condition between training dataset and target simulations is exactly the same. Now let's talk about a more realistic scenario where an operating condition between the training dataset and target simulation is similar but slightly different. For example, I trained a neural model based on the training dataset where the initial temperature is 850 Kelvin, and then I used this model for the target simulations where the initial temperature is 900 Kelvin. In that case, as you expected, the AI-based model shows a larger discrepancy with the ground truth value because ANN model is inherently vulnerable to extrapolations. This result indicates that if we don't have a training data set over which an operating condition is exactly the same as the target simulations, it would be difficult to directly use that kind of data set for our machine learning-based research. And here, transfer learning can be a good solution to resolve this issue. The main idea of transfer learning is that instead of training two independent machine learning models, the knowledge of the pre-trained machine learning model is transferred to a target task such that the overall performance of target machine learning model can be enhanced using only a sparse data set. And the goal of this study is to investigate how to transfer the knowledge of the pre-trained model to a target task. In this study, we use a regularization-based transfer learning approach. The overall idea is mainly introduced in this paper, and it is quite simple. Let's say that the parameters of the pre-trained AN model is denoted by WS. Then, when we optimize the parameters in the target machine learning model, W, the difference between W and WS is imposed as a penalty term. So this is similar to a regularizer, but the parameters obtained from the previous task are used as a reference value. I'd like to call this model as a written like here, and we focus on this identity matrix. That means that when we transfer the knowledge of the pre-trained model, the importance of each of the parameters is considered to be equal. But we thought that there are parameters more or less important to affect the objective function. Therefore, our idea is that if we can identify the importance of each parameter to source functions in the source task and use such information as a weighting factor, the overall performance of transfer learning model can be further improved. Here, we use a Hessian matrix to identify the sensitivity of each of parameters. If we have a simple neural net model like here, I can construct the Hessian matrix like this. And the diagonal terms of the Hessian matrix represent the curvature of the loss with respect to the parameter. So the first transfer learning model we introduce is to use the diagonal term of the Hessian matrix as a weighting function, and it is called as TLD. And the second transfer learning model is to use the full Hessian matrix called TLH. In the full Hessian matrix, the off-diagonal terms represents the interaction between parameters. Therefore, if we use the full Hessian matrix instead of using an identity matrix, we can also transfer the knowledge about the interactions between parameters. It looked to be fine, but this method had a critical drawback, which is associated with the size of the full Hessian matrix. The dimension of the full Hessian matrix is equal to the number of parameters, so it will be infeasible to apply this method to a deep neural net model. In this sense, the last transfer learning model we introduced is the compromised version of TLH. The last transfer learning model, called TLB-DB, uses block diagonal terms of the full Hessian matrix. This model assumes that the interaction of the parameters within the same layer is more important than that across layers. This model can reduce the memory significantly compared to TLH, while the interaction between parameters are still considered. Therefore, we propose three different transfer learning models on top of the baseline transfer learning model, where identity matrix is used for transfer knowledge. All right, then I'd like to talk about the data set used in this study. The first case is a toy problem. The input of the ANN model is the mole fraction of methane, O2, and temperature. And the output of the model is the consumption rate of the methane, which is represented by this global reaction. And here, the value of the alpha is said to be different between source and target task, such that we are dealing with a slightly different objective function. In the source task, where I make a pre-trained ANN model, I use a large enough number of training samples, 51Q, to train the neural net model. You can see the profile of the data set like here, O2, methane, and temperature, and this z-axis shows the output of the data set. And in the target task, the number of training samples are forced to be low, like only 64 samples, such that the corresponding ANN model will be likely to show a noticeable amount of errors. Then we leverage the knowledge obtained from the source task by using different transfer learning models, and we evaluate the amount of performance gain obtained from these transfer learning strategies. All right, so I'd like to show one of the results for this toy problem. And this figure shows the normalized root mean scalar error profile as a function of the magnitude of the regularization parameters by using different transfer learning models. And this black line shows the overall result predicted by using a baseline transfer learning model. As you can see here, when we don't use any transfer learning strategy where the lambda equals 0, then the overall error becomes 10%. But if we transfer the knowledge at some extent, then we can drop the error by 2%, which is significant. So this result demonstrates that utilizing the pre-trained neural net model to a target task is a simple but effective strategy. And it is also found that using a diagonal terms of Hessian matrix, which is TLD, shows only a marginal increase of performance as compared to the TLI. Whereas the result of TLH shows a noticeable performance improvement compared to TLI. That means that the interaction between parameters are important knowledge to be transferred. And it is also found that the TLBD and TLH exhibit a similar level of the best achievable normalized root mean square error. That indicates that interaction between the parameter within the same layer contains the most of the valuable information. And we also performed the another study by changing the number of training samples M in the target task. And we found that the primary factor for decreasing the error is just by using the transfer learning strategy. So you can see that without transfer learning model, the requisite number of training sample that makes the NRMSE below 1% is where the number of training samples becomes almost 10 to 4, whereas if we use a transfer learning approach, we only need order of 100 training samples to make the same amount of errors. And it can be seen that when with the overall data sparsity issue is more highlighted, the advantage of using the Hessian-based transfer learning approach, such as TLH and TLBD, shows a noticeable further improvement, as you can see in here. Whereas as the number of training samples becomes larger and larger, there's no discernible differences between TLI and the other method. And the second example is a more realistic case where the ANM model is used to predict the chemical source term of the 9-species hydrogen air system. And my goal is to capture the chemical kinetics of 2D non-premix hydrogen versus air flame within a single vortex structure. And here the air temperature is set to be 1800 Kelvin. And I generated the training dataset by using the 1D flame dataset, but at the same operating condition. Then, since the 1D dataset does not consider the effect of curvature on the flame structure, we can guess that the error of the ANM model for this target task will be very high, especially within the vortex region. Then we use various transfer learning models by using a pre-trained neural net model, which is based on the another 2D dataset, but with a slightly different air temperature. And this figure shows the 2D ISO contours of one of the outputs of the neural net model, which is the formation rate of the H. And this is the ground truth solution. And if we just use the neural net model trained by using a 1D dataset, you can see that there's a lot of discrepancy between two, especially within the vortex structure, because the 1D dataset does not take into account the effect of curvature on the output. And when we use a baseline transfer learning model, you can see that there's a significant noticeable amount of improvement, especially within the vortex collision. But I also noticed a slight error at these lesions. But if we use curvature-based approaches, and we can get a much better, slightly better result as compared to TLI, again demonstrating the effectiveness of using Hessian-based transfer learning approach. And we also compare the output of the another quantity, which is the hillage rate. So this figure shows the scatter plot of the hillage rate predicted by the ANM model and ground truth value. And as you can expect, if we don't use any transfer learning model, and there's a lot of discrepancy between ANM model and ground truth, especially for the case where the vorticity is very high. Whereas with the use of the baseline transfer learning model or Hessian-based transfer learning model, we can get a much better result as compared to the baseline transfer learning model. So yes, so from this study, we can highlight the advantage, the importance of using the transfer learning approach by utilizing the pre-trained neural net model. And we also address the further advantage of using a Hessian-based transfer learning approach. That is the all of my presentation. So thank you for your attention.